Welcome to Chapter 3, Linear and Quadratic Functions. Linear and Quadratic Functions. And Section 3.1 is Properties of Linear Functions and Linear Models. So we're basically taking the y equals mx plus b ideas we had previously, and you're good at graphing lines and interpreting m and b, slope and y-intercept. And we're pushing those into the setting of functions. So in this section, we'll define and graph linear functions, somewhat repetitious with things we've done in the past, fortunately. We'll determine whether a linear function is increasing, decreasing, or constant, and build linear models from so-called verbal descriptions. First, a formal definition. A linear function is a function of the form f of x equals mx plus b. Functions that are not linear are called nonlinear. You already know f of x equals mx plus b, or y equals mx plus b, has as its graph a line. The slope is m, the y-intercept is b, the domain is all real numbers. But you may hear this term of linear function used in another way in your future math classes. So this definition is only valid in Precalculus 1, maybe in Calculus 1 as well. But there'll be other settings when you take linear algebra, for example, a sophomore level class, where the idea of a linear function will be somewhat different from what we've defined it as here. In those settings, a linear function in our realm would be of the form f of x equals mx. The b would have to be 0 to satisfy the definition of linear in some other settings. But for us, we've just got x's and y's. We're in some sense in 2 dimensions, and we can make sense out of graphs of functions, which are lines, and such graphs in here are called linear functions. Let's illustrate with that warning on the table. Let's illustrate in our setting this idea of linear function with an example. Okay, consider h of x equals negative 2/3 x plus 4. Determine the slope and y-intercept, h. Use the slope and y-intercept to graph the linear function, h. Okay, well, h of x is already of the form mx plus b. It equals negative 2/3 x plus 4. So they want the slope. Slope must be negative 2/3. Y-intercept must be b equals 4. So 0, 4 is the point on the graph that corresponds to the y-intercept. And to graph this, use the slope and the y-intercept to graph the function. We've got one point and we got a slope. Well, let's use that slope to find a second point, as we've often done. So the slope was change in y over change in x, rise over run, as we informally put it, delta y over delta x, as we symbolically put it. And we know that equals negative 2/3. Negative 2/3, so we could take delta x equals 3 and delta y equals negative 2, for example. We could take delta x equals negative 3 and delta y equals positive 2 also, or an infinite number of other things. But choose some reasonable values for delta y and delta x, and that allows us to find a new point on the line, x plus delta x and y plus delta y, based on the point xy equals 0, 4. So x plus delta x would be this 0 plus this delta x, 0 plus 3, right? Y plus delta y would be y equals 4 plus delta y equals negative 2 would be 4 plus negative 2, giving us another point, 3, 2. So we've got 2 points. Given 2 points, we can graph the function. Here's the intercept, 0, 4. Here's that other point we found, 3, 2. Given these 2 points, then the graph of the line must look a lot like this. So 2 points is sufficient to graph a line. They gave us a point and a slope, as we've commonly done. Actually, they give us a point and an intercept. The intercept is equivalent to a point on the y-axis, the y-intercept. We've repeatedly used this idea of finding a second point using the slope. Let's check this real quick. We got 2 points on this line. Speaking geometrically, the slope should be rise over run. It should also be negative 2/3. Let's start at this point. Let's rise negative 2 and run 3. And that exactly produces this other point. I could also rise positive 2 and run negative 3, right? With the negatives being downward or to the left. And that'll take us from this point to that point. If I start here and rise negative 2 and run 3, that gives me another point over here. In fact, I'm pretty confident this other point, 6, 0, I bet you that's the x-intercept, as we could easily verify by substituting the coordinates of that point in. But they wanted a graph, we gave them a graph. We'll come back to that same example again and exploring connections and some of these other things. Theorem 3.1.a is the average rate of change of a linear function. It says linear functions have constant average rate of change. That is, the average rate of change of a linear function, f of x equals mx plus b, is delta y over delta x. We had discussed average rate of change before. For the setting of a line, it's just the slope of a line. Let's illustrate that idea with the same function as we had previously, continuing number 18. We had h of x equals negative 2/3 x plus 4. Determine the average rate of change. Well, we just said the average rate of change is simply the slope. So the average rate of change of this function is negative 2/3. The average rate of change of a linear function is a constant. Think of average rates of change as steepness. For arbitrary functions, they can be steeper in some places than they are in others. Lines always have the same steepness. They always have the same slope, in other words. So with that interpretation of average rate of change as steepness, it's not surprising. It's related to the slope. In fact, it equals the slope and it's constant. Let's look at another example where they give us data. Okay. They say determine whether the function values given in the table could be associated with a linear function or a nonlinear function. If it could be linear, determine the slope. And they give us a bunch of x and f of x values, effectively x and y values. Okay, we just saw that a linear function has constant average rate of change. So I tell you what, let's use that result, Theorem 3.1.a, and find the average rate of change based on pairs of points. Let's compute this for consecutive pairs of points. Let's find the average rate of change from here to here, and here to here, and here to here, and here to here. If all of those are the same, then we must have a linear function. If any two of those are different, we don't have a linear function. Okay, so we'll take those points, first and second point, second and third point, third and fourth point, fourth and fifth point, and calculate the average rate of change, the change in y over the change in x. We're just calculating the slope of the line through these 2 points effectively. It corresponds with respect to the function f or f of x to the average rate of change of that function over the appropriate interval. So we do the computations, change in y over change in x. Let's do the first one in detail. The others we'll just look at. That would be changes from 1/2 to 1/4, 1/2 minus 1/4, that's the change in the y values. Change in the x values correspondingly would be -1 minus -2, -1 minus -2. Let's see, 1/2 minus 1/4 leaves us with 1/4 divided by -2 minus, sorry, -1 minus -2, that's -1 plus 2, it's 1, it's 1/4 over 1, that's 1/4. Similarly, we compute those other average rates of change. They're not all the same. In fact, the rate of change here is 1/4, then 1/2, bigger, then 1, bigger, then 2, bigger. So this function has an average rate of change that's getting greater, getting bigger and more positive. If we were to plot the points, and we don't have to, they didn't ask us to, we'd see those points tracing out a steeper and steeper function as we move to the right, as indicated by these average rates of change. They're not all the same, so we're not dealing with a linear function. We must be dealing with a nonlinear function, given these values. Back to the notes. We know from the definition of slope that we gave in section 1.3, lines, the line section, that a positive slope line has a graph that's going uphill and a negative slope line has a graph that's going downhill, as read from left to right, as we always do. So this allows us to discuss uphill and downhill, or increasing and decreasing, in terms of slopes for linear functions. In Calculus 1, you'll have a way to talk about increasing and decreasingness in terms of something else, and it will apply to more sophisticated functions than just linear functions. Theorem 3.1.b says a linear function, f of x equals mx plus b, is increasing over its domain if its slope is positive. Yeah, it's going uphill if its slope is positive, and that's what increasing means. It's decreasing over its domain if its slope is negative. It's going downhill when read from left to right. And it's a constant over its domain if the slope is 0. If the slope is 0, the x term disappears and you simply get f of x equals b. To illustrate that, let's recycle the last little part of number 18. Consider h of x equals negative 2/3 x plus 4. Determine whether this linear function is increasing, decreasing, or constant. Excellent questions. This is a piece of cake. Well, the slope is negative 2/3. We saw that in part A. Of course, it's the m and mx plus b. And negative 2/3 is negative. So this is a decreasing function. So this function is decreasing on all of its domain. So easy enough to determine increasing and decreasing this for linear functions. It's simply a matter of the sign of the slope. Returning to the notes. Let's do another example. Return to the exercises. Okay, here's two functions, two linear functions. F of x equals 3x plus 5. G of x equals negative 2x plus 5. And they give you a handful of things to do. Solve f of x equals 0. Solve f of x is less than 0. That'd be where f of x is negative. Solve f of x equals g of x. Solve f of x is greater than or equal to g of x. Graph y equals f of x and y equals g of x, and label the point that represents the solution to the equation f of x equals g of x. And this last part, the solution of the equation f of x equals g of x, that's where the two lines intersect, where their y coordinates will be the same. So we'll solve for x and setting the y coordinates equal to each other. It'll give us a single point that lies on both lines. First, to solve, f of x equals 0, take the function 3x plus 5, set it equal to 0, take the 5 to the other side and divide. We get x equals negative 5/3. Easy enough. Solve f of x is less than 0. Well, we'll do the same thing, only with an inequality. F of x is less than 0 means 3x plus 5 is less than 0. Take the 5 to the other side, divide both sides by 3. This time you get x is less than negative 5/3. A little more interesting, f of x equals g of x. We'll set f of x equals to g of x. That's 3x plus 5 equals g of x is negative 2x plus 5. Set those equal to each other. Bring the negative 2x to the left, giving us 5x. Subtract 5 from both sides. We get 5x equals 0. So x equals 0. So the function values are the same when x equals 0 and when the function values, it looks like they'll both be 5. Right? If x is 0, both function values will be 5. And that's how we get the function values equal at that point. So the point 0, 5 will lie on both. That'll be part of the discussion when we graph the thing. Part D was solve f of x is greater than or equal to g of x. Okay, that's the same kind of thing, except we'll replace the equality with a greater than or equal to. Same manipulations, divide both sides by 5, and we get x is greater than or equal to 0. In terms of an inequality, we could also, of course, express that in interval notation. So there's the algebraic things they wanted us to do. Now they want us to graph y equals f of x and y equals g of x, and label the point representing the solution to the equation f of x equals g of x. Okay, graphing lines, I want 2 points on both lines. So we've got the point 0, 5. We saw in was it part D that f of x equals g of x gives the point 0, 5. We got 0 is the x value, plug 0 into both of those functions, and you get an output value of 5 in both of those functions. So that gives us this point in green. The solution to the equation f of x equals g of x corresponds to that point where the lines intersect. Now, let's, with a little less delta x, delta y fanfare, let's find second points on those lines using the slope. F of x, 3x plus 5, has a slope of 3. All right, how about we do this? Let's go down 3 and back 1. Rise -3, run -1. That'll give this second point here. Both of those are negative. The ratio is -3 to -1. That's still a ratio of 3. So the slope is 3. I choose to go down and back because if I go up 3 and over 1, it does give me another point on the curve, but it's off the little scale that I've got. You want to go, what we're looking for, a ratio of 3 to 1. We could go down 6 and back 2 and find yet another point on the curve, but we only need 2 points. So let's go down and back, down 3, back 1, ratio of +3 in terms of rise over run. That gives us a second point. In blue, the f of x curve must be as given. Passes through the green point that's on both curves, the blue point that we determined from the slope. 2 points determine a line. There you go. There's the line. For the red line, the g of x function, g of x is -2x plus 5. Okay, let's use the slope of -2 and the fact that this green point is on that curve to find a second point. Rise over run is -2. How about we rise -2, go down 2, and run 1 and go 1 over. And that'll give us this point here. Then the green and the red points are on the graph of g of x, and we can sketch out g of x based on that. So computationally, we've done that delta y, delta x stuff and chosen particular delta y's and delta x's based on the slopes of first 3 for this linear function and then -2 for that linear function. Picture look okay? This is a blue line. It's got the correct kind of slope. Yeah, it's got a slope of 3. And it's easier to see by starting at this point, rising 3 and running 1. Slope of 3. It goes uphill. It's positive slope. All that part checks out. This line here goes downhill. Yeah, the slope is -2. For every unit, it goes. Every unit it rises. How about it rises -2? It runs +1. One way to view it, and it goes downhill at the proper rate. Its slope is -2. It's going downhill when read from left to right because the slope is negative. So just to quickly check things out, this looks like it's probably the right graph. It contains the right points, and checking it at the end, these lines have the right kind of behavior in terms of slopes. Back to the notes. Let's look at some building of linear models from verbal descriptions. That's how the book describes this stuff. Maybe call your attention to the supply and demand example, example 5 from the section. And let's do a couple of examples in the supplements that are somewhat related. Number 38 says, The monthly cost C in dollars for calls from the United States to Germany on a certain phone plan is modeled by the function C of x equals 0.26x plus 5, where x is the number of minutes used. Part A. What's the cost if you talk on the phone for 50 minutes? Part B. Suppose your monthly bill is $21.64. How many minutes did you use the phone in this way? Part C. Suppose that you budget yourself $50 per month for the phone. What's the maximum number of minutes that you can talk? So how many minutes makes the bill $50? And part D, what is the implied domain of C if there are 30 days in the month? Okay, this last question is a little weird, but we'll do it anyhow. Okay, they've given us the linear function. Part A, what's the cost if you talk on the phone 50 minutes? That's x. We'll substitute in 50 for x, 0.26 times 50 plus 5, simplify, becomes $18. Part B, suppose your monthly bill is $21.64. How many minutes did you use the phone? The number of minutes is x. So that question is C of x equals 21.64 units or dollars, implies x equals what? So we'll take C of x, 0.26x plus 5, 0.26x plus 5, and we'll set it equal to 21.64. Solve for x. That'll be the number of minutes that produces a bill of this size. Subtract 5 from both sides, trying to get x by itself. That'll produce 16.64 on the right-hand side. Then divide by the coefficient, 0.26. That will produce x is 16.64 divided by 0.26. In the absence of a calculator, I'm happy to say that's the answer in minutes. Let's simplify it so it makes some bit of intuitive sense. And upon simplifying that, you find it equals 64. So x equals 64 minutes will produce a phone bill of that amount under this model. Part C. Suppose you budget yourself $50 per month. What's the maximum number of minutes you can talk? All right, same idea. We're setting the cost function equal to 50 minutes. As we did in part B, that's taking the cost function, setting the cost equal to $50, setting the cost function equal to $50. 0.26x plus 5 equals 50. Subtract 5 from both sides, reduces the right-hand side to 45. Divide by the 0.26. 45 divided by 0.26 is what x equals, and that's roughly 173 minutes. This is quite similar to part B, except the numbers turned out a little bit messier, I guess. I didn't give decimal parts of minutes. Part D, what's the implied domain of C if there's 30 days in the month? Domain of C, here's C. C of x equals 0.26x plus 5. X is a number of minutes used. So how many minutes are there in 30 days is effectively the question. The value of x is a number of minutes used. So x can be at least 0, can't be negative, in other words. So we could not use the phone at all, in which case x equals 0. In 30 days, you could turn the phone off and talk for 30 days. How many minutes is that? Is what we need to decipher. Well, we'll take 30 days and just do some change of units. We'll multiply it by 24 hours per day and multiply that by 60 minutes per hour. Remember, we went through this in the appendices. Units cancel just like numbers do. So here we've got days, and here we've got days in the denominator, so we can cancel the days. Here we've got hours in the numerator and hours in the denominator, so we can cancel those. And in fact, you'll be left with minutes is the correct units. 30 times 24 times 60, thanks calculator probably, this is 43,200 minutes. So that's all the time there is in all the minutes there are in a 30-day month. So x could be anything between 0 and 43,200. So the domain of C, implied domain of C in such a situation is a closed interval from 0 to 43,200. Another example. also related to cell phones. A cell phone company offers an international plan by charging $30 for the first 80 minutes plus 50 cents for each minute over 80 minutes. Write a linear model that relates the cost in dollars of talking X minutes, assuming X is greater than or equal to 80. Use that function to calculate the cost of talking 105 minutes or 120 minutes. All right, none of these word problems can be very sophisticated in this section because all we've got at our disposal is linear functions. So it's got to boil down to some kind of mx plus b manipulations. Okay, $30 for the first 80 minutes. So we're assuming you use this at least 80 minutes. So you're definitely going to get $30 and then 50 cents for each minute over 80 minutes. So X is a number of minutes, C of X, where X is a number of minutes. If we introduce that as the cost function, we're assuming X is greater than or equal to 0. So the domain, by the way, then is 80 to infinity, including the 80. We're told to assume X is greater than or equal to 80. Okay. Then we've got that $30 for the first 80 minutes. You might call that fixed cost. It's in some sense related to fixed cost. And then there's 50 cents for each minute over 80. Well, we're letting X be the number of minutes. The only thing that's affected by the 50 cents per minute is the number of minutes X is greater than 80. So we need to take X minus 80. That's the number of minutes over 80. And that's what's affected by this 50 cents per minute charge. Producing the cost function, $30 plus $0.5 times X minus 80. Units will be dollars because it's cost. Minutes play a passing role. X is measured in terms of minutes. This cost of 50 cents is it's dollars per minute if we put a unit on that. And that gives us this function, which we could multiply out. I'll tell you what, let's just leave it like that. I think it's a little bit easier to see what's going on if we leave it in that form. You want to distribute the 1/2. Go at it. That'll produce a negative 40 over here. You'll get a negative 10, 30 minus 40 and negative 10 plus the 50 cents then. But remember, we're assuming X is greater than 80. I think I want to leave that expression there. All right, so suppose we did X equals 105 minutes. That's greater than 80, so it's in the domain of the function. Then we'd have the cost C of 105, which is 30 plus 0.5 times 105 minus 80. That's 105 minus 80 is what, 25? That's the number of minutes over 80, right? And it's 50 cents per one of those minutes. So we get 30 plus 1/2 of 25. That's $12.50. And the total sum is $42.5. If we had 120 minutes, we'd do the same type of thing. Plug 120 in. 120 minus 80 is 40. That's the number of minutes over 80. Yeah. 120 minutes is 40 minutes longer than 80 minutes. So we pick up the 40 over here. The 50 cents per minute's the charge on that, plus there's the $30 for the first 80 minutes. So we get 30 plus 1/2 of 40. That's 30 plus 20, and that's $50. And that's the content of this section. So we're looking at linear and quadratic functions. Linear functions of necessity can be very complicated. We're just redoing the y equals mx plus b stuff. Next section, I think, is building models based on data, section 3.2. We're going to skip that one and go straight to section 3.3, and I think start looking at quadratic models. But I'll see you in section 3.3. Have a nice day.